Good morning, good afternoon, or maybe evening, everyone, wherever you are. Welcome to the second IEEE International Workshop on Harnessing the Data Revolution in Networking. My name is Anwar Walid. I'm from Nokia Bell Labs. I'm one of the general co-chairs. My other co-chair is Dan Pei from Tsinghua University. This workshop is a follow-up on our last year's successful workshop. As we know, networking has been undergoing significant transformation enabled by softwareization, virtualization, and cloud computing, which enable new capabilities and services, but at the same time making end-to-end network automation more complex and challenging. Now enter recent advances in AI ML and the availability of data from network telemetry and instrumentations at various layers, and we have opportunities to solve really challenging networking problems. So today we have brought together industrial practitioners and academic researchers to share ideas and visions around these topics. We'd like to thank Zili Zhang from the ICNP Steering Committee for his help and guidance in organizing this workshop. And now I'd like to introduce my co-chair, Dan Pei from Tsinghua University. Dan,
thank you, Anwar. All right, thank you, Anwar. Yeah, here we also want to thank the ICNP conference organizer for making this hybrid meeting possible. So, as a workshop, we just utilize what the conference provides. So that made our workshop organization much easier. And as Anwar introduced, I'm the other co-chair. And we would also want to thank all the workshop organizers this year. And Tamer, do you have the next slides? Oh, yeah. We have a few co-organizers that includes the TPC co-chairs, Tamer, Hashid, and Batos. And Tamer is from Virginia Commonwealth University, and Hashid is from Juniper Network, and Batos is also from Virginia Commonwealth University. And we thank all the hard work by our organizers and also a lot of volunteers. And in particular, we greatly thank our TPC co-chair Tamer and Hashid and Batos for bringing together the great program today. So now I'm going to hand over to Tamer, please.
All right, let's see. Okay, I hope that you can hear me, everyone. Well, is my voice clearer now?
Yeah.
Yes. Okay.
Very good.
I confirm. We can hear you.
All right, perfect. So as Anwar mentioned, good morning, good afternoon, or even good night, or good evening to everyone, given the different time zone. So I'm actually, it was my pleasure or honor to really participate and co-chair the TPC for this second iteration of the HDR-Nets workshop. I would love to also thank a lot of volunteer works behind the scene in reviewing and recommending papers that we will enjoy during this workshop. Just a quick note about some statistics about the HDR-Nets. Second iteration, we kind of received a kind of moderate number of papers where we have like 10 full submissions. We assigned 3 to 4 reviewers for each paper. We accepted 5 papers out of these 10, like 50%. And we also invited another 2 papers talks to be part of our full day program. So we have a full day program. We have actually 2 keynote talks, one in the morning that will following this opening immediately, and then we have one after the lunch, afternoon one. Again, the times, as you can see, it's based on the Central European summertime. So please accommodate for the time zone differences. So we have 3 technical sessions. We will start with after the first keynote, we will have immediately the first technical session, which will be a short, just including of 1 paper. Then we will break, and then we will have the second technical session, which will be about noontime, and we'll have 4 technical papers. Then we will break, a long break for the lunch, and then we will immediately start with the second keynote, and then we will have the 3rd technical session, which including 2 papers after the second keynote, and then we will have a coffee break, and then we will have a panel discussion, which will have 4 interesting honorable panelists, moderated by 2 moderators at the end of the workshop, and then we will close around 7 p.m. again with the Central European summertime. So starting with our program, the first keynote today is by Professor Archan Misra. It will be about collaborative edge-based machine intelligence, promising and challenged. Just quick information about Professor Archan. Sorry, bear with me because switching between the WOVA and the other things is kind of hard handling multitasking here. All right. So Professor Misra is actually a professor of computer science and the vice provost of research at the Singapore Management University. He's a director of the Singapore Management University Center for Applied Smart Nation Analytics, which stands for CASA, which is developing pervasive technologies for smart city infrastructures and applications. Professor Archan has led a number of multi-million-dollar large-scale research initiatives at Singapore Management University, including the Live Labs. I'm pretty sure that many of you heard about it. Live Labs Research Center, and he's a current recipient of the prestigious investigator grant from Singapore National Research Foundation for Sustainable Man-Machine Interaction Intelligence. He has over than 20 years research career spanning both academics and industry. He was at IBM Research and Belcor before moving to Singapore Management University. Professor Archan has published on and practically deployed technologies spanning wireless networking, mobile and wearable sensing, and urban mobility analytics. His current research interests lie in the ultra-low energy execution of machine intelligence algorithms using wearable and IoT devices. He also holds a PhD from the University of Maryland at College Park, and he chaired the IEEE Computer Society's Technical Committee on Computer Communications from 2005 to 2007. Without further ado, I would love to hand the floor to Professor Archan for his keynote. Let's see.
Hi, Tamer. Just want to make sure that
let me close my video and also. So Archan, can you share your slides? I believe I have to stop sharing. Sorry. Okay, and now we should be able to share. right. Archan, you're on mute if you.
Hello. Hi, Tamer. Can you hear me?
Yeah, perfectly.
Yeah, we can hear you.
Okay. And can you see my slides now?
Yes.
Okay, we could probably make this work. Shall I get started?
Yeah, sure. Whenever you want.
Okay. Well. First of all, I mean, if I'm not wrong, Tamer, it's like a 4:40 in the morning for you.
That's
so
right.
It's just amazing. Well, I guess this is how things have been going this entire year. So first of all, thanks to everybody for tuning in to listen to me. My name is Archan, and I'll talk for about 40 minutes or so, 40 to 45 minutes. It's a pleasure to have this opportunity to talk to you folks. I understand I've been to several ICNPs, not in the last couple of years, but I think the last one I went was 2017 or 18. And the reason, I wanted to preface this presentation by saying that this isn't so much a networking presentation. It is about sensing, about sort of ML at the edge, but I think it has some overlaps and some implications in networking as well, and I've tried to highlight those. So I want to start off by acknowledging, a bunch of people who actually do all the hard work, the postdocs, the PhD students, several engineers, and just to lay out the agenda, what I'll be talking about, you'll hear this term CMI, Collaborative Machine Intelligence. It has, the idea that I have is that a lot of this will be executed at the edge instead of the cloud, primarily for latency reasons. That's the focus of a lot of my own work. It's around interactive applications. But what I hope to do, and just give you a preview, one of my beliefs is that the next big challenge in sort of network systems and sort of sensing systems in general is to solve what I call the battery challenge. I don't think we can scale anymore if we still require batteries to operate or power sources, power outlets to operate most sensors. So over the last couple of years, I've been looking mostly at how we can slowly transition, through systems innovations. Of course, we won't go purely battery-less, but the idea is to reduce the power consumption or energy profile significantly to the point where we might actually be able to make these devices last much longer. So without sort of, let's get into the heart of it. I want to do a little bit of an introduction of myself, not so much just to introduce me, but I think it'll help you explain to you folks the journey I've been on and the sort of points of view I take. So this is sort of the encapsulates my stint in Singapore. I joined here exactly 10 years ago in October of 2010. So for the first 5 years, Tamer mentioned, I was working with this Live Lab Center, for example, and the focus was a lot on mobile sensing and analytics. So the challenge, the research thrust there was, sort of the classic things around using inertial sensors, using gyroscopes and accelerometers and so on, to try to deduce various kinds of what I say locomotive activities, whether you're walking, whether you're queuing, climbing stairs and so on. And I would say that a lot of that work has now become mainstream, in commodity products today. Over from 2014 to 2018, I think gradually my focus began to shift towards wearable devices. And in particular, the two wearable devices that I've looked at extensively are a wristwatch or a smartwatch, and afterwards a smart glass, but mostly a wristwatch. And the opportunity that watches obviously provide is the ability to now begin to sense a different kind of physical activity. These are activities that are related to gestures. So we did work on, tracking the ability of people, what they're eating and how much they're eating using a watch, or if you're going to a retail store, how are you trying on a product, how are you interacting with the product, and so on. But more than that, which is not so relevant, the big change from a phone to a watch was we went from about a 3,000 milliamp hour battery to about a 300 to 400 milliamp hour battery. So it's a tenfold reduction in the energy capacity. So naturally, we now had to start making the algorithms more energy efficient and sort of at least ensure that a wearable device would last for a day. But starting, I would say actually in early 2019, maybe very late 2018, my focus again began to shift when I kind of recognized through a variety of projects we've done that the bottleneck wasn't so much the cost of the sensor or the accuracy or the ML models built to do activity recognition from the sensors. In many cases, it simply was that we couldn't get the sensors to last long enough. And in particular, we stopped deploying sensors in buildings, in parks and so on. And I realized that really the way forward, the most precious resource right now is energy. So a lot of my research has pivoted to understanding how to make battery-less sensing possible. And a particular piece that will connect to the theme of this workshop today is going to be around understanding, how new modalities of that video analytics, how can you optimize it to take, to be both low energy and also take more judicious use of the bandwidth that's available. So that's a quick journey, and I wanted to share that with you. I'll breeze through the first two slides because this is really more of a retrospective. So I was mentioning that a lot of my work has been around sensing and wearable sensing. So here's an example. You have this sensor that you see right in the middle over here. I assume you can see the cursor. So this is a weight stack machine. You put a simple magnetometer and accelerometer on the weight stack. And as people exercise and move it up and down, you can build models that can understand the weight, how much you're lifting, what kind of exercise, how many repetitions. It can classify the exercise. Is a bicep curl or tricep, tricep exercise or a lat pull down and so on. And we can do this quite accurately over time. So let's just move on. So we went from, so that was an IoT device attached to an equipment. But now, so that IoT device, actually if I go back over here, this device would last, say 3 weeks on a battery operating while it was continuously running. And that's not so bad. But now, we started to get a little more ambitious over the last year. So this is work where we say, we want to measure the activities that you're doing when you're lifting a dumbbell. Now, the issue that, the transition that happens is, from one weight stack machines, you have hundreds of dumbbells and people use them interchangeably, right? You do one set with a particular weight, you can transition to a different weight right after. And so the focus that I tried to do over the last year or so has been around the notion of using a wearable device. So these in-ear, again, accelerometer, gyroscope signals from your head, along with an IoT device mounted on the dumbbell. And if you combine these two, we build a system that can actually do live tracking of your exercises, and it can identify all these kinds of mistakes. So these are mistakes where you curl your wrist, which you're not supposed to do during a bicep curl, or you droop your shoulders, or you don't do a full range of motion, etc. Now, again, for the purpose of this audience, that's not so important. What is important is, through this journey, this IoT sensor on the dumbbell, the wearable sensor, the Earable, is your own personal sensor. You wear it, you're listening to music, you're working out, you go charge it. But the IoT sensor on the dumbbell can last maybe 100, 120 hours if continuously used. It has sleep modes. But even if you change it to it lasts 3 weeks to a month, now you have the situation where you have hundreds of these dumbbells in a gym, and you're going to have to constantly refresh the batteries on them. So this kind of gave me the insight that as we move to a more pervasive environment where the sensing platforms are becoming smaller and being attached to everyday devices, we can't have pure wearable sensing and we can't have pure infrastructure sensing. We need to combine them. And we realized that the energy overheads are just too prohibitive. Even if we build those systems, you can't just operate them and ask somebody to go in every 2 weeks to keep changing batteries. So as I motivate the rest of the talk, I want to make one other observation that I've been sort of having over the last 2-3 years. That's the second point over here. Now, for the last 2 decades, if you've been doing sensor networking, you've operated under a basic principle. The principle is communication is very expensive, computation is cheap. So that's why we do all kinds of in-network computation, compressive sensing, and so on. Reduce the volume of data that needs to be transported. And you don't worry, you try to do a computation as close to the device. Now, I think the general claim is obviously still true, that the cost of transmitting a bit of data wirelessly is still much more energy expensive than doing one flop of computation. However, in a more aggregate sense, there are sort of a paradigm shift that is slowly but surely happening. So first, over the last few years, because of all the great work that I think our community has been doing, we've been building a lot of ultra-low energy first personal area network protocols and now wide area network protocols like LoRa and so on. So the communication energy per bit of transmission is dropping, and there are other new technologies coming, especially for short range communication, where it's beginning to be much lower than it used to be. Now, on the other hand, if you look at what's happening with computation, especially when you talk of sensors, everybody talks DNN these days. You're talking about sort of processing data. And the thing with DNNs is, previously you would extract some features, do some statistical aggregation. Now you're running these deep neural networks at 150, 200 million parameters. So given a single image, the amount of computation you do on the data to do, on that image frame to do object detection is not trivial any longer. So in fact, there are some situations, not a lot, but we already have situations where it's actually cheaper to transfer the data from a sensor device to an edge node and do the processing on the edge node than do the processing on the sensor data on the sensor device itself. And when I say cheaper, I don't mean from the cost of the sensor. I actually mean from an energy perspective, from a battery depletion perspective. So I wanted to make this point that I do think that over the next decade, we're going to be rethinking how networked sensor systems are architected. I think we're going to see a lot more of transferring data to common endpoints where you have certain redundancies, certain other benefits of collaboration. That's part of my talk today. When you have those things, you can take advantage of them, and you're not shying away from transmitting raw or sort of semi-processed information over a wireless network. So that's kind of like the background. I don't think to this community I need to sort of give this sort of spiel here. So the resource bottleneck, obviously we know with Moore's law, everything's increased. The battery energy has not increased. The density of battery capacity has really been growing sublinearly. Now, the other point I wanted to make today is, again, to you folks, I don't think this is surprising, but I think the numbers itself are very stark. I mean, just, whether or not, even if you're off by like 50%. So today, as of even 2020, apparently 80% of the data generated in the world actually ends up in a data center somewhere, whether you're, you're streaming WoWA or any other platform, Zoom and so on, it's actually hitting a cloud network. But apparently in just 2 years, or let's say 3 years, there's a complete flip. So 70% of the data never actually hits the data center. It gets consumed at the edge, discarded, you extract the insights, maybe you have fast control loops at the edge, and then you just throw away the data. So I think, this dawn of the edge network is a really important thing in terms of how we design communication networks and how the interplay between AI at the edge and sort of network and resource consumption, energy consumption at the edge plays out. So with that, I wanted to share with you my research vision. Again, I'm giving a lot of background vision here because I think that's perhaps more useful to you than the specifics of the research projects, although I'll get to them very shortly. So the goal I have is making sensing cheap and abundant. Now, again, if I can sort of get on a pulpit and say, if you look at all the big industrial revolutions that we've had in the world, they've all been, all of economic revolutions are about taking a product that is either scarce or expensive, one of the two, usually both. And the moment you make it cheap and abundant, you have a transformation in our society. So we had that with the steam engine, we had that with electricity. There were certain types of resources. And the AI age that's happening right now is we have made computation cheap and abundant. I think you'll all agree that now, we don't think of, buying GPU racks, storing things, running petaflops of computation, even in a university research lab. What hasn't become cheap and abundant, in my opinion, is the energy resource. So if you look at the quadrant on the right, what you see is I have these two axes. I see, most sensor systems operate under sort of two paradigms right now. So you have things like the RFID tags. They are battery-less. We have battery-less. We have tags that can measure occupancy and temperature and so on. And indeed, but what do we do with that data? We don't actually analyze. You don't run a DNN on data that's coming out from an RFID. You probably do occupancy and aggregation, some statistical, mean, median, outlier filtration, and that's about it. Now, on the other hand, if you look at devices like your smartwatch, a smart glass, a smartphone, they're doing a tremendous amount of analytics these days. You're recognizing gestures, you have LiDAR sensors, you're trying to do 3D point clouds and estimation, fusion, and all of these kind of things, but they're very complex and they're very energy hungry. So what we want to do is to move into this quadrant where we'll be able to do these kind of complex operations, but ideally, for applications like telepresence and collaborative robotics, but we'll be able to do it with the energy cost that typically RFID tags have. So that's sort of my vision, that I want to drive the sensor consumption of the power consumption of sensing devices, such as wearables, etc., sort of a twofold decrease in magnitude. So today, we take anywhere between 10 to 100, 200 milliwatts of power on these platforms. We want to bring it down to 100 to 500 microwatts. And we also want the sense making now, which is migrating to the edge, which has already happened. But you want to support that with not just low latency, but again, low power in the execution. So I think that's part of the dialogue that I'd be hoping to have with all of you today after I finish my talk. So with that, with that sort of the background, now how do I think one can go about, sort of realizing this vision? So I think what is really important is the notion of collaboration among these edge devices. Edge or pervasive devices, they actually have to collaborate not just in their sensing, they have to collaborate in their inferencing as well. And this collaboration will be either between wearable and edge, or multiple IoT devices or static devices like cameras and an edge network as well. And for today's talk, I want to go a little bit breadth first, but I also want to have a little bit substance to it. So I kind of distilled a whole variety of different research projects that are going on, and I picked two. I want to talk about this ability to do distributed triggered sensing, which allows us to operate sensor devices, even wearable devices, which harvest energy wirelessly and then operate in a battery-less fashion. I'll talk about that, some early results on that. And that'll have some implications on sort of the design of low power downlink and uplink networking links as well. But then I want to preserve most of my time after that talking about the CMI, this collaborative, machine learning based intelligence. And I want to show that how collaboration can actually improve accuracy, save energy. And I won't get to talk much about latency, but my belief, or in other work, we show that you can actually decrease the latency of processing as well. So with that, let me start off on the first piece over here, which is the piece around the distributed and triggered sensing. So one of the things that we've been trying to look at over the last couple of years is the notion of repurposing wireless. Now, in particular, I wanted to say, if you look at the research going on in our community, wireless started off, the whole Wi-Fi revolution was about Wi-Fi as a data transmission medium, right? It was for networking and transmission. But first, on the left, you see, we've already seen so much cool work on repurposing the same wireless medium, radar, etc., as sort of this passive sensing medium. We can understand, capture breathing rates, movements, even sort of, do composition analysis from RFID phase shifts of shapes and liquid content in it. There's been a lot of work in like Mobicom and Mobisys, etc., on this topic. Now, recently, of course, in addition to just being, so it was communication and sensing, but I think wireless is also really a promising, it's not an exclusive, I want to make it clear. There's always a role for like, photo cell-based operations and solar cells. There's vibration harvesting. But I think in general, in the pantheon of renewable technologies, wireless transmission, not just very short range, can also become a very interesting possibility. And that's something that I'll briefly talk about. So one of the things we did a year and a half ago was we built this wearable device. When I call it wearable, it's not a wristwatch form factor, but you could put it on your wrist, and it has no battery. It has a supercapacitor to do transient charge harvesting, but it has no battery, and it can operate an accelerometer in an indoor environment, collect the acceleration data, which can then be translated to understanding gestures and hand motions and so on. And the way you do that, the big picture is like, if you just see this animation, the person's got the thing. When they come in, they send a single ping packet to an access point, a commercial Wi-Fi access point. This is the key. After you estimate the angle of arrival, you can now beamform what we call power packets. So we are transmitting packets on the wireless network. The whole goal is to transfer energy, RF energy, to the wireless device. Now the wireless device is harvesting it. And then when it also has a motion trigger. So when it's a zero energy motion trigger, when your hand moves, it activates the accelerometer. it collects the data, and afterward, it transmits it back to the access point. So the key breakthrough over here, if you look at the graph on the bottom, this is the amount of energy you harvest at a distance x, which is 1 to 1.5 meters from a commercial access point today, which is an omnidirectional transmission. And you can see it's kind of drops, even at a distance of a meter away, it drops to below 5 microwatts. So at that point, and it's below like 1 microwatt at a 1.5 meter distance. So this harvested energy, it exists in the ether. It's just way too low to do anything useful with it. However, we built a system, and the whole idea, and again, these details kind of don't matter so much, but there is a RF harvesting circuit. There's a motion trigger, which is a simple magnetic sensor. Your magnetic field changes when your hand begins to move. That triggers the processor to actually trigger the sensor itself, the microcontroller to trigger the sensor. So we build this thing. On the access point side, of course, it's actually a fully 802.11 compliant access point. We built it off a warm board, so we had to actually stitch them together. So one of the interesting things that came out is here you see an 8 antenna access point. Now, if you realize, well, I guess I'll talk about it over here. If you see that the first axis on the left over here, it shows the amount of harvested energy. This is at a distance of 1 meter as a function of the access point. So of the antennas on the access point. So with 8 access points, we're now, instead of harvesting less than 1 microwatt, we're able to focus a beam and therefore harvest over 250 microwatts. Now, even if you look to the graph on the right, you see you go 3 meters away, which is not, that's a non-trivial distance to be away from a regular access point. You're actually able to harvest over 30 to 50 microwatts. We've actually since then gone up closer to 100 microwatts since these graphs came out. And in particular, what I wanted to show is, again, this is a very limited, admittedly toy scenario. But you see at the bottom, there is a person working on their laptop in an office-like environment, the access point on the wall. They're about, 2 3 meters away. And we did this experiment where the person would tap on their laptop while they were wearing this thing, or they would, read a newspaper or go to a whiteboard and work on something. And the accelerometer would be selectively triggered to collect this data. When you do that, let me hide this thing, I guess. Okay, so when you do that, we kind of measure the delta total energy. So what this graph illustrates is the energy harvested minus energy spent. And you see across 4 users, their usage was quite different. It's actually net positive, which means that the total harvested energy we had, not only was it able to do the sensing, we actually had enough energy left over a period of 1 hour. Now, the reason this becomes interesting is, just imagine we're now demonstrating the possibility of doing sort of continuous triggered vibration sensing without a battery at all. But it's built on the ability to closely couple the interaction between the wireless device and, in this case, the Wi-Fi access point. But let me just continue and bring in a little bit networking perspective to the problem. So more recently, we've been looking at the low power downlink. So the problem of what we had before was that we didn't know if the device is moving, it has to generate a ping packet to the Wi-Fi network, because the Wi-Fi AP has to know in what direction you are so it can beamform better to you. Secondly, because we were using a very low power radio, again in the 2.4 gigahertz band, to make the uplink transmission, so the transmission of the sensor data energy efficient, it's kind of like LoRa. We don't do any CSMA, we don't do any sort of reservation. You turn on the radio, you transmit the data. So that works well when you have only just one such device. So let's consider now IoT devices like this. But if you have a whole bunch of devices, you activate them, then they turn on and they're going to collide. So what we decided to, we started to look at a wake-up receiver. Now, traditionally, we've been using wake-up receivers. The purpose of a wake-up receiver is a very low bitrate, low power channel. The radio is always on, listening for a, hey, wake up signal. And what it does is that then it triggers the main radio transceiver to wake up, right? So the main radio transceiver is the high bitrate communication link, high power, and so on. Now, what we did was we actually repurposed the wake-up receiver channel to be a low-power downlink for a variety of purposes. So the first thing was, if you look at the graph here, So it's a wake-up signal. So if you're targeting a particular IoT device, let's say in a in a factory-like setting, you can send a signal that will wake that thing up. But after that, you actually can transmit configuration information in that wake-up signal itself. So you don't have to wake up the main radio. And secondly, because by using these LPURs, which are like, things available in the ARM processors, for example, you can actually decode these signals and set registers and so on without waking up the main processor. So you save even more energy. But perhaps most innovatively, what you also do is, suppose I have 10 devices that I want to get a piece of information from. What's the temperature from all 10 of you? So what I do is I send a wake-up signal by turns to each of, I wake them all up simultaneously, one Wi-Fi transmission signal. But in the wake-up signal, I actually provide the schedule of their uplink transmission. That's what this thing indicates. So I tell them slots. So I say device 1 in slot 4, device 2 in slot 2, etc. So I provided an implicit TDMA schedule that these devices can now follow. They wake up their uplink transceiver, and they transmit only in their slot. So with this mechanism, if you look at the graph on the left, what you see, this is when the wake-up receiver starts working. In the conventional approach, to parse the data to understand which slot to use, the main radio would spike up. You get about 40 milliwatts of power spike. But if you do this, you don't start the microcontroller, but you use the LPUR, you actually can save even more energy. You can operate literally below like 10 milliwatts on this transmission. And what the graphs, we don't have time to go into detail, but what these show is we're comparing wireless LAN, power save wireless LAN. There's 802.11ba, which is the wake-up protocol for wireless LAN networks, with our low-power downlink protocol. And what you see, the energy per byte that we achieve, even for an uplink transmission, as a result of all these changes we make, is actually 1 order of magnitude lower. It's 2 orders of magnitude lower than power-saving wireless LAN, and 1 order of magnitude lower than 802.11ba. And as a result, you can actually get a lot more bits across. So the thing I wanted to say over here is just share with you evidence, excuse me, that we now have the advances in technology that are allowing really efficient transmission of data, triggered transmission of data on the uplink, coordinated by a central node like an IoT device or an edge device. And at the same time, the edge device is also being repurposed to do energy transfer to these battery-less devices. So I think there's a great opportunity, in my view, to really do these sort of pervasive deployments where you have these selected power nodes, like on today's access point, for example. But the access point is a mechanism that enables both very low power data transfer as well as fairly efficient energy transfer. Now, you might wonder, I mentioned the example of just, okay, it's like a few microwatts, etc. But I think there are other people around the world that have been looking. In particular, I'm showing you this paper from UVCOM 2019. It's work out of Rutgers University. Now, what you see on the bottom here, they actually have these transmitters. There's a whole array of them on the roof. So they're spaced maybe, I think a meter apart or so on. So very different than us, not a single access point. And they were operating in the more 900 megahertz range where the propagation drop-off is much lower. Even so, the point is by orchestrating the phase shifts of these things, they're actually able to deliver power precisely to a very small area, and they can deliver up to about a 1 milliwatt of power anywhere within this sort of warehouse room, selectively by adjusting the power. And I think that's a very interesting possibility. So in our own group, we've been working at what happens when you have multiple Wi-Fi access points and how do we coordinate them. And the reason this becomes exciting is we have clearly moved into the area of cloud RANs, right? Today, the radio access networks, the Wi-Fi access points are no longer independently operating. They're centrally controlled over a cloud. And I think once we begin to have this intelligence, we can repurpose the Wi-Fi or the RF network in general to be not just used for data transmission or energy efficient data transmission, but at the same time as a mechanism for energy transfer. So that's one of the first claims and observations I wanted to make with this work. So with that, what's kind of a takeaway and reflection? So the reflection is you have, I think in the future, going to have this combination of passive RF sensing. You're going to have battery-less wearable/IoT devices. I really think it's a possibility in some cases, but you need this edge machine learning to do the multimodal inferencing, because you're going to get data from a variety of sensors, some from, say, sound, some from video, potentially being ultra low power devices. We need to be able to combine them, which is where I'll move to the second part of my talk, which will be looking at how the communication network interacts with the ML piece, which is the sense-making piece on the edge device. So with that, let me move to the second part of the talk. So the collaborative MI or CMI have been what I want to talk about. Yes, we understand, you know, I'm using vision as an exemplar. I want to say I'm not a vision researcher, so we just take off-the-shelf DNNs. The principles that I'll articulate today, I believe, will carry over to like sound sensing or any other kind of modality you want, you know, including things like radar and LiDAR, which are coming down the road. So we understand that the problem is DNNs at the edge, they take low, very long latency. So they could take like up to half a second to process a frame to do, say, object detection. They also have low accuracy. Now, this is important because, you know, when you do pervasive deployments, they have cameras. You don't know how, you know, they're going to be positioned properly. They have occlusion, they have bad lighting, so they have environmental artifacts. And most importantly, if you're deploying these devices, you're going to deplete their energy really dramatically fast, especially if you're talking of a vision algorithm. So just to set up the setting of what I mean by collaborative machine intelligence, we've been working with this notion of, let's say, a campus network camera system. It's doing monitoring of people and objects on a campus. So you have these bunch of cameras. They are connected maybe wirelessly. They don't have to be peer-to-peer. They could be connected to an edge network. And the first observation I make is, you know, if you see in the top, you see this is camera A's view. So there are two people here. Camera A can only see the purple person and not the green because the green is obscured. B can see both of them. Now, interestingly, so the whole idea is that if B was able to share its knowledge, that I can see these two people, or I have two bounding boxes over here. If I can share that with A, then A's inferencing accuracy should go up. I mean, big picture, that would seem to be obvious. Now, there is a disadvantage anytime you go into the collaborative model, because fundamentally what you're doing is you're adapting your processing logic to take inputs from other peer nodes, and you're trusting those peer nodes. So that's where I say if you have an adversarial network, so suppose this is C lies, and even though it can see both, it actually says there is no green person over there. So obviously, if you have a malicious node, you're actually going to get worse inference because you're trusting it blindly. But what I will try to show now is that by adjusting the collaborative sensing pipeline, I won't get into the malicious part of the security aspects of this behavior today. I'll just leave that out of scope. But I want to show that in a well-behaved network, by taking advantage of the spatial and or temporal overlap from the diversity of sensors available, you can actually improve accuracy. And you can do this without needing to retrain the model. So again, before I go further, I want to sort of make it explicitly clear that any results I show after this, there is no custom training of the model to any specific deployment. We're taking off the shelf, you know, SSD, LOV3, if you're familiar with these type of technologies. We're just taking them and we're adjusting on the runtime, the parameters on the operations of the model to make it improve its performance. You'll see that shortly. So the design goals, as I said, is no retraining. It's backward compatible. So in other words, the big vision is you have this camera A and B. If camera B will stop working tomorrow, A should just continue. It should degrade to its baseline, which is its non-collaborative mode. And obviously, when people collaborate, this sets up this trade-off, right? And again, goes back to the trade-off that I said at the beginning. Now, if you want to collaborate, you have to share something. So you have to share some intermediate state of the DNN, or you have to share the bounding boxes that your camera found. Now, my claim, and I will demonstrate this, is to show that yes, these things require bandwidth, but by judiciously selecting the appropriate digests, you can be very parsimonious in your use of bandwidth, and you can significantly outperform, you know, the bandwidth cost is swamped by the significant gains you get in accuracy, etc., from such collaboration. So as a big picture, again, if you go back to this is how vision models today largely work. You have low complexity models, mobile net, etc. Things built for mobile, they're more one pass on the network. Usually don't have regional proposal networks and so on built into the DNNs. But they have relatively lower accuracy, but they work relatively fast. Then you have high complexity models, YOLO V3, MassPower, CNN, etc. And what we're hoping with the collaboration is to move the operating curve somewhere there. We will pay a little more in latency because we now have to pay the latency of network transfers. But on the other hand, we will get a significant jump in accuracy, maybe not as much as the high complex models, but something that enables us to perform much better. So we're trying to close the accuracy gap with this collaboration. So I want to give you very rudimentary examples. Now, these are not the, if you, in the language of patterns, these are not the preferred embodiments of the collaboration. What I want to do is to introduce the concepts. I'll get to the more complex models shortly afterwards. So one way to collaborate that you can see over here, imagine this is the primary camera. This is what it sees. A secondary camera or multiple secondary cameras, they can run their object detector. They can send you bit masks where the white rectangle is. This is where they think they saw a human being. We can get those in, and one way of fusion is take that and go out to the output layer of your network. So in particular, in these networks, you actually have bounding boxes proposed, then you do a non-maximal suppression to reduce false positives. That's where you can provide these other priors. So it's kind of like a Bayesian fusion. This is one approach. See? And of course, to do that, there's a few details here. You had to do some spatial transformation because the perspective of the other camera is different than yours. But these are things that are pretty standard in sort of video processing today. Now, the other alternative is, instead of providing just at the output layer, you can give these inputs at the input layer. So now, instead of a 3-channel RGB image, you might have like a 5-channel image where the other 2 channels are these black and white masks coming from the other cameras. And you can run through and see, can you identify where the people are? And again, I am deliberately skimming a little bit with which pets, pretty standard data set. We've primarily been looking at pets and wild track as 2 different sort of data sets on the spectrum. What we show is this collaborative SSD, the one on the right, as opposed to the one on the left, they both actually significantly outperform the baseline. They give you about a 10% increase in accuracy. Now, the accuracy itself is, this is a mean precision score if you want to be very pedantic about it. But what is happening, one of the key insights that we realize is, because the cameras have different perspective, in this camera view, for example, there's a person over here, they'll appear very small, and this camera might miss it. But from the other camera, we should say positioned here, this person over here is actually larger. So it has a higher chance of reliably detecting it. And if you bring that prior in a judicious way, you can actually boost up your accuracy considerably. Now, that's like at the end. So I gave you the binary choices. You either do it right at the end of the pipeline or right at the beginning. But it turns out that you can actually do things much more efficiently and effectively by doing things at the intermediate stages, because the disadvantage of doing things at the end or beginning is, you're losing a lot of information. So in particular, you see 2 cameras, and those blue and red lines are basically stages of the DNN pipeline, so convolutional layers, max pooling layers, etc. So one approach you can do is that, as I said, the same person in camera 1 is small and camera 2 is much larger. And what you can do is you can take the outputs at the feature maps from the appropriate layer. I'm generalizing this right now. And then you can pass this to the corresponding sort of anchor boxes for this camera. Because usually a larger anchor box here will translate to a smaller anchor box here. And as a result, this pipeline will see an improvement in detections. What is happening over here, now this is kind of interesting because if I transmit from the earliest layers, we know that the volume of information, all the convolutional layers, that volume is too large. So you're going to pay a high networking cost. On the other hand, if I get to here, you're progressively having less and less information or less and less bits. So I'll be able to transfer with much lower bandwidth requirement and get the higher improvement in accuracy. And again, I have to do a little hand waving here in the interest of time. What we show is over a well-optimized network right now, this is the first cut, we get about a 3 to 4% increase in the true positive rate. So this is not humongous yet. but this is 3 and 4% over not the baseline, it's over the collaborative baseline I've introduced. So we are getting a still additional 3-4% improvement that's coming from the ability that we are actually exploiting all the hidden information and the detailed information in the hidden layers. Now, we can actually do something even better, which is once we extract these features, we realize that not all features matter, because if you're looking for people, there are certain feature maps, this depends on the convolutional filter used, that are more discriminative. And what we find is that if you use a combination of the feature values, so these are the activation map values at the convolutional layer, along with the location and scale of the anchor boxes. And if you run a regressor, so this is like a separate model that takes these feature maps from here, and it predicts that I think the anchor boxes over here need to be boosted because I'm pretty confident that I see a person. So I'm doing this not after I've run through my pipeline. I'm doing this at the first layer where even I haven't finished my own processing, but I'm transferring some of the state information to be fused with the nth layer of the other DNA. So this is a little subtle. If you have questions on this, please ask me afterwards. What this is doing is, it's kind of like, if you think of the concept of pipelining. Now these two cameras can operate in completely synchronized pipeline fashion, because otherwise, if this guy needs this output as its input, it has to wait until this camera finishes processing, then it takes as an input. Here, you know, they start processing synchronously. The output generated here, by the time it transits the network and gets here, this guy has finished processing. So we suffer no loss in frame rate. We have very minimal demands on bandwidth, but we actually significantly improve the accuracy of these systems. So we're getting, you know, from about 80%, we have gone to 95% accuracy by taking advantage of the collaborative information, collaborative sharing of the information. So this was the improvement in accuracy. I also want to bring out that collaboration actually helps save fundamentally the sensing energy. So again, one of the basic principles we operated on was that we had these two cameras that had the shared common region where they were overlapping. They were observing it from different perspectives. So if you look at these two cameras, if you run a re-ID network, each of them are identifying two people at the top at the same time. And on the basis of that, without any ground truth, etc., they can auto-learn their estimated areas of overlap. So that's step one. So a camera operating independently, just bootstrapping itself, will learn that, oh, the left rectangular portion of my field of view overlaps with camera 2. Now there is a role for the edge to play. And again, what I want to say is we've demonstrated with real networks that you can actually compute this estimated overlap to be pretty accurate. Not 100%, our IOU or intersection over union scores are about 88% or so. So you can estimate the actual overlapping region. Now comes the kicker. What do we do with this overlap? So the whole idea is that in the overlapping region, I can reduce my sampling resolution. So in the non-overlapping areas, I can still continue to do an HD camera sensing. In the overlapping areas, maybe I can reduce my resolution. The hypothesis or the belief is that because I have additional information from another camera, even if both of us are low resolution, together jointly, we should be able to offer the same performance as a single high resolution image. That's the concept. So what you see on the left is this collaborative detection filter. So you have these two cameras. They first estimate their overlaps. They find the coordinate translation between them. And then in runtime, when they're operating, when you get input, you get what we call a mixed resolution image. I'll come to that afterwards. So you get some part of this, of your image is at low resolution in the single frame. This part may be low, this is high resolution. You combine them and you have a DNN that tries to do a joint inference. And these two graphs are actually very important. So the green line, sorry, the orange line over here and the yellow line, which is kind of hidden here, and these two, these are what we call the baselines, where you see that you actually, this axis, you're reducing the resolution of the image. And what you can see is that if you can actually collaborate with the right spatial resolution, your average precision accuracy stays even when you go down from a 512 cross 512 to a 70 cross 70. Oops, sorry again. So that's like almost a 50-fold reduction in the number of bits you're sampling, number of pixels you're sampling. You still maintain, whereas if you're doing things as a baseline, you drop precipitously because you get a fuzzy image, you can't recover the objects. We're running an object detector over here. And we've done this across different cameras, different occupancy settings, and so on. But the key point is to give you a demonstration that indeed our hypothesis was true. That by taking advantage of the spatial overlap, we can reduce the resolution, the data needed to be transmitted from each camera to the edge, and we can still get the same performance that we did with a single independent camera operating. But this is not just a savings in bandwidth, because that's what you get. The previous graph was about communication savings, because you don't have to transfer as many bits. Now we realize, and this is work just going on, you can actually go ahead and modify the camera itself. So we took a Pixie 2 camera. This is a very low power camera with a dual core processor, very little low memory. And what we did was, while acquiring the image, because you have to spend a certain amount of energy in acquiring an image itself. And the way it operates is you have the CMOS sensors, they get charged, you have to go read each pixel, you have to do the A to D conversion, etc. But now if we go ahead and we modify the firmware of this camera so that if you say on the top left or the left half of the image, do it at half the resolution of the right, then you will skip over the pixels. You won't even do the A to D conversion. And what we see with that, and this is a somewhat misleading graph, indeed as the resolution reduces, the energy consumption of the number of millijoules in the sensing energy, this is not the data processing, this is not the transmission, the sensing energy drops. Now you can see it doesn't drop linearly with the reduction. That's because, as many other papers have shown, you also have to simultaneously adjust the clock frequency, because otherwise, you have a lot of idle cycles in the camera processor itself, which reduces the efficiency. So we've done that, and essentially, again, I don't show this in this graph. Now we can, with the 300 by 12, 200 resolution, we can actually get 1.5 millijoule power consumption. So down from 5.5 millijoules to 1.5. So about a 80% reduction in the energy in the sensor itself. So the key message over here, using this power of collaboration and collaborative ML, you can improve accuracy, you can save energy in the sensing process itself, and you can save energy in the transmission because you don't need to transmit as many bits. So overall, this is actually a substantive amount of savings that you're doing without sacrificing any accuracy at all. So I'm going to stop here because I'm sort of looking at the time, and I'll do one last thing and then stop. But I want to summarize over here that this collaborative ML approach, I think it requires new DNN architectures. I think as to the ML community, but most importantly is this vision that based on the network, we need to adapt the functionality of the DNN. We might tell one camera, oh, your network bandwidth is very congested, so you send me even a lower resolution picture. But I tell the other camera, you send me a higher resolution picture in real time. But because by fusing them, I know I will get the same quality output. So again, what I want to say, I want to propose this paradigm of network-aware collaborative DNN. I think there's a lot of promise to this technology. So the last thing I wanted to end with was talking about edge computing. I talked about 7 out of 10 bytes will never see a data center. Here's my valid proposition about the edge. Today, I see the edge primarily as an isolated offloading computation offloading platform. So if 6 of us get on the edge, each of us will get containerized. We will not be, we'll have our own little sandbox. We'll have computation offloading. You can run, speech recognition or vision algorithms on the edge, do it faster, get the responses back. And that's great. Nothing wrong with that. We're doing that for low latency. We're doing this for data privacy in some cases. That's all useful. But to realize the vision that I taught, which is the collaboration among sensing devices and the automatic network-aware adaptation of the ML pipeline, the edge actually needs to be more. And that's what I call the cognitive edge. And this is where the edge actually is a matchmaker, a broker for IoT and mobile devices. So imagine you have all these distributed cameras and say microphone sensors. They don't even know with whom they should share. They don't know with whom they have overlaps or spatial temporal correlation. So what they do is they keep sending some very low bandwidth summary statistics to this edge device. The edge is the one that looks through them, does sort of pairing, if you think like bipartite graph matching style algorithms, and says, oh, I realize these two cameras and this particular microphone, you guys have actually spatial overlap. So when one camera sees it, the microphone actually picks up conversations or sounds from objects in that vicinity. So you should collaborate, and then it instantiates this DNN. This is why I say machine learning as a service. It's creating the DNN on the fly that is taking inputs from these three devices, and running the collaborative machine learning paradigm that I just talked about on them. So this becomes more of an autonomous system, because again, if you have to manually provision these thousands of devices, it's just not going to scale. So you want the auto discoverability of collaboration opportunities and the auto configurability of the collaboration parameters. And I think that's where a collaborative edge, which to me is a totally different positioning of the edge. And I would love to hear from you guys on this. I know there are people from networking companies and so on, but I'm a big proponent of this. I've had conversations with several people who've been very receptive to this idea. So it offers a bunch of services. So the challenges that I wanted to put out, you have to find these useful spatial correlations. We have to have the edge. If you want to do collaborative, with the cognitive edge as supporting this, we have to find ways to enable trusted interactions, because one of the weaknesses, which we have done nothing on so far, is one malicious node could take down the system, because by injecting false information, it could sort of foul up the analytics that we're doing. And of course, we have to do these dynamic workloads, because I didn't mention it explicitly there, because some camera may be running on a battery, maybe its network bandwidth is low, so you want to compensate for that by automatically adjusting the resolution or the transmission rate or frame rate of another camera. So we need to be able to do these dynamic adaptations, sort of twinning between the network and the machine learning pipeline. So I think the edge as a dynamic matchmaker and orchestrator is an important concept that I would like to advocate. With that, I'm going to stop. I think I'll just let you read this slide for a second. My big vision is that we need to dramatically reduce the power consumption, at least 100-fold. We need better orchestration and collaboration among these devices. I think I'm going to stop here, and let's just figure out the way to stop sharing, so then I guess you can all see me again.
Right. Thanks, Archan, for this interesting talk, and given the virtual live we're in, I hope that we give you a round of applause here. Thank you. Right.
Yeah, that was a very dramatic applause. Thank you.
So we have a few minutes for a couple of questions. Please, I think you can unmute yourself and you can speak up for questions. Yeah, I don't know.
Yeah, so Tamer, do you want me to respond to the question that has popped up on the question chat first?
Absolutely. Yeah.
Sure. So thank you for that question. So there's a question, just in case, for everybody's benefit, do you think federated learning can help to save energy? Now, I want to clarify something first, that actually in the thing I presented, there was actually no collaborative or no change in the learning itself, because you actually see that what I was talking about was the runtime inferencing. So we were adapting the parameters, adjusting the the bounding boxes or the anchor boxes or the feature maps. They were being done at runtime based on the sharing of state between DNNs. Now, having said that, I do understand the notion of federated learning, but federated learning primarily has been done, from my recognition, it's to distribute, is to shield your own data. So it's more of a privacy enabling concept that allows you to incrementally refine your model by taking advantage of model refinements on other platforms. So I think that has a role to play. I don't quite immediately see how that saves energy during the runtime, so not during the training, but during the runtime inferencing. Because to me, the energy saving at runtime is coming from this ability to trade-off between the fidelity of the resolution of the data from one sensor versus another, but by adapting the ML pipeline itself as well. Now, if I may just expand on that, perhaps the intent of the question, the model that I just described was we had, if you think there are two sensor nodes, they send their data to a common edge. And all of this collaborative inferencing happening at the common edge. You could arguably say that there may be situations where the inferencing itself is distributed. It goes back to these two nodes. So in that case, they'll have to share information among themselves, again, over a network. Now, in such cases, it is possible that they can also learn jointly together to decide that there are certain types of information maybe the other guy has no advantage. So for example, again, just indulge me, this is a thought experiment. I'm a camera. I actually share both my driveway and my porch, both of these spaces with another camera. But it turns out that my porch, I'm actually good enough because it's a very well-lit area. I don't need the information from the other camera. But for my driveway, which is more dimly lit, I actually benefit from collaboration with the other camera. So if I can learn that in runtime, I can actually go and tell the other camera, you don't need to share information about my porch, for example. I mean, I hope I've answered that question.
All right, thank you, Archan. Any other questions, please?
Hi, Archan. I have another question. I think actually majority of my question has been answered already by your answer to the previous question. I'm wondering whether the collaborative cameras that you talk about, how to be administrated by the same owner. So, if not, how do you coordinate? How do you address the data privacy issue? I know this is probably not really a machine learning problem, but that's if you want to make this realistic, this is something to think about, right? Yeah.
Actually, that is a very important question. So I want to give you a two-part answer. First, honestly, we have not tackled the privacy issue ourselves. I mean, I think that's very important to know, but I'll still give you some layered answers. So as you pointed out, our assumption right now, like we said, it's a university campus camera network, all administered by the same domain. So collaboration and sharing among these nodes, it's administratively enabled, not a big deal. You have secret keys that you exchange and so on. But I think in the spirit of what you're saying, down the road, I can totally see, you buy cameras from company A, other sensors from company B, or even in shared spaces. If you think, we've been thinking and not doing any work on this. If you want to bring this notion back into a home environment as well, you buy devices from Huawei or you buy devices from Samsung, and you want the home gateway device to be able to orchestrate, to be a trusted repository orchestrating between these things. So I think that answer is not completely clear. There will need to be a relationship of trust, and that's an open question. However, I actually want to address the privacy question a little bit. And that's one of the reasons why you see, if you look at the pipeline, when we said, what does the other camera share? In the other camera, it actually shared only a black and white mask of a bounding box. It didn't actually share any of the pixels that it observed. So there was a layer of privacy. It shared some metadata. It didn't actually share the data. Similarly, if you look at the subsequent stage, it shared some feature maps with you. It didn't share the actual raw pixels. It shared some intermediate state of the DNN. Now, one could argue that, I know there's been so much work on GANs and so on that you can recover images. There's adversarial models that can recover information from that, which we haven't covered. But fundamentally, as a first cut answer, that's one of the reasons why we're not sharing the raw data. We're actually sharing the intermediate representations, which one could argue are not as privacy sensitive as the raw data.
Great. So in that sense, do you see federated learning application in addressing the privacy issue down the road?
Oh, absolutely. I mean, most definitely. I think the issue, see, one of the open questions, again, everything we've done today has assumed that you're not doing any custom training for any of these models. Now, there's nothing to stop us from actually doing custom training, and I think the performance will definitely improve at that point. And when you want to do custom training, I think this is an open challenge, because if you think what federated learning, the classic example is, you know, you are trying to train your model to detect, say, walking versus running. You want to take advantage of my data and my pre-built model and to make it more robust, right? This is sort of the classic example of federated learning. But what I haven't seen work, or I'm not aware of, is where do we do federated learning when we have to do collaborative inferencing? So I actually need your data or some features from your data to build my model. You need features from me to build your model. But the core federated learning concept doesn't actually share features of the data. It shares the model itself. So I think that's an open question. We have not done any work on that.
Great. Thank you so much.
Sure.
Thanks, Archan. For the sake of the time, please, if you have any further question, you can do that over the WUVA platform Q&A. And thanks again, Archan, for this interesting talk. There's a lot of interesting questions, and we might follow up offline on that. Thanks again.
Well, thank you so much, Nadeem. Tamer, I really appreciate it, and especially for waking up at 4 o'clock to listen to this.
Absolutely. All right. So moving on with our program, so we're starting our first technical session, which will be short right before the break. Let me just sharing the screen. Okay, it's too slow. Apologize. Okay, so we have one paper presentation. It's a semi-supervised stacked autoencoder approach for network traffic classification. It will be presented by Aouedi. I hope that I'm pronouncing your name correctly. Just a quick introduction for you. Sorry for this. Yeah. So Ons received her master's degree in computer science from the higher school of digital economy of Manouba, ESEN in Tunisia. She is currently pursuing her PhD degree at LS2N, University of Nantes in France. Her research interests include the area of network management using machine learning techniques. So without any further ado, I will stop my sharing and will hand the sharing and the control for you, Ons.
Can I share my screen now?
Yes, please go ahead.
Okay. It's okay?
Yes, we see it. Perfect.
So, hello everyone. I am Ons Aouedi. I am a PhD student at University of Nantes. So today I will talk about our recent work titled Semi-supervised stacked autoencoder approach for network traffic classification. So this work has been done with my PhD supervisor, Kandaraj Piamrat from University of Nantes, and a bachelor student, Dhruvjyoti Bagadthey from IIT Madras, India. So the outline of this presentation, I will start with an introduction, and I will talk briefly about the motivation of this work. Next, I am going to present the semi-supervised traffic classification approach. And after showing several results, I conclude this presentation. So let's get started with a short introduction and motivation of this work. So the large majority of users rely on the internet to communicate with others, to do shopping and watching movies. Also, the huge number of smart devices will exceed the world population. Besides the communication, the internet has become a crucial component for millions of business. So all this made the internet used by the general public, and accordingly trigger research in traffic and application. And that's why the operator need to understand the type of traffic carried on the internet, and maybe traffic classification can be a promising solution for this task. So as the importance of traffic classification increases, so several techniques have been proposed over the years. Some of the techniques we have pro-based traffic classification, which is the most simple technique. Science analysis of the packet header is used to identify only the raw number, and this corresponds to the real raw number. But the application can use dynamic raw number or POR associated with other protocol to hide from network security tools. So to avoid the total reliance on the semantic raw number, deep packet inspection has been proposed. So this technique inspects the payload of the packet, searching for patterns that identify the application. So this technique checks all packet data, which consumes a lot of CPU resource and can cause a scalability problem. That's why many research work started to use machine learning in network traffic classification in order to avoid the limitation of deep packet inspection and POR-based traffic classification. So machine learning here used as an alternative approach to classify the traffic using the characteristic of the traffic. So as shown here that in the field of machine learning, a broad distinction could be made between supervised learning used when we have labeled data and supervised learning used when we have unlabeled data, and semi-supervised learning when our data are partially labeled. But in reality, a lot of datasets are partially labeled due to many reasons, as the application emerges every day, so it's not possible to have all the flow labeled in real time, where this unlabeled data can provide informative characteristics. So that's why the semi-supervised learning can be a promising solution for network traffic classification. The semi-supervised learning is a combination of supervised and unsupervised learning, used when the dataset consists of input-output pairs, but the output values are not known for certain observation, and this reflects the situation of most of the network dataset. Thus, the contribution of this work is that our model takes advantage of both labeled and unlabeled data to implement a classification task. And by taking advantage of unsupervised learning, our model extracts robust feature automatically without the need for an expert to extract feature manually. Now I will present our semi-supervised traffic classification approach. So I'll show here that our model, I'll show here that we have developed a semi-supervised learning using unsupervised feature learning using labeled data and supervised traffic classification using labeled data. So here both labeled and unlabeled data. So here both labeled and unlabeled data have been used to extract more valuable information and make a better classification. Also, these architectures integrate feature learning and traffic classification in one architecture to avoid human intervention and time wasting as maximum as possible. To do this, we have used the staked sparse autoencoder, which is a complex architecture of autoencoder. Then, to improve the performance of the classification and to avoid the overfitting, we have integrated the dropout and the noise encode hyperparameter into our model. So as a reminder here that the autoencoder is an unsupervised learning algorithm divided into 3 parts, which are encoder, code, and decoder. So the encoder obtains the input and converts it to an abstraction which is known as code. Then the input can be reconstructed from the code through the decoder layer. And it uses nonlinear header layer to perform dimensionality reduction. So to obtain a better performance than classic autoencoder, we have used the staked sparse autoencoder, which consists of layer-based pre-training and the global fine-tuning process. The layer-based pre-training helps the deep neural network model to yield much better local initialization than random initialization. And the global fine-tuning process optimizes the parameter of the model, which greatly improves the classification task. Also, the sparse constraint on the header layer can help to capture a high-level representation of the data. So, as shown here, that in the staked sparse autoencoder, each layer is in this stage is trained like an autoencoder by minimizing its reconstructed error. So when all these layers are pre-training, so the network goes to the supervised fine-tuning stage. At the supervised fine-tuning stage, a softmax layer, as shown here, added to the encoder layer of the unsupervised learning for the classification task. Then, to prevent the identity transformation and avoiding overfitting, we have injected the part and the noise encode into our model. So here, dropout is a technique that aims to help a neural network model to learn more robust feature and reduce the interdependent learning among the neuron. It removes the neuron from the network along with all its incoming and outgoing connection, and the choice of this neuron is random. Also, the denoising autoencoder was proposed to improve the robustness of feature representation. It is trained to reconstruct a clean input from a corrupted version of it in order to extract more relevant feature. So this corruption of the data is done by first corrupting the initial input to get a partially destroyed version. So some results here. So the data set used in this work was collected in network section from University of Columbia. It was constructed by performing packet capture at different hours during the morning and afternoon over 6 days in 2017. But for facilitating computation, we have used only the traffic collected from 1 day. So as shown here that 70% of the data are labeled and 30% are unlabeled. Also, it consists of 54 applications. The application like Facebook, Dropbox, Google. Also, it has more than 400,000 examples with 87 features. Some of this feature, so I can't present all the features. So some of this we have source port, destination IP, destination port, timestamp, flow duration, and so on. Also, our data are unbalanced, so that's why we have used the undersampling technique to balance our data. Also, we have separated the labeled data into 80% for training and 20% for validation and testing. And to obtain the optimal model, we need to find the different hyperparameters that maximize the accuracy of the model. So in this context, several configurations have been done, and based on this are presented in this table. So as shown here, that the result in the bold text obtains the best result. So we have varied the number of the layers, the number of neurons, the learning rate to find this result. And according to this result, we have tried to improve the classification performance. To do this, we have injected the dropout and the noise encode hyperparameter into our model. So and test the effect on the accuracy of this model. So as shown here, that the rate varied between 0 and 0.05. And we stopped when the performance started to decrease. So the best classification obtained when we have the noise rate and the dropout rate equal to 0.03 and 0.02 respectively. Then a comparison has carried out between the staked sparse autoencoder and staked sparse autoencoder with this hyperparameter. So as shown here, that this hyperparameter improves our model with 2.2%. Also, to verify the performance of this model, we have compared it with 3 reference classifiers, which are random forest, SVM, and decision tree. So these classifiers are built on top of our staked sparse autoencoder without the softmax layer, in order to benefit from its automatic feature extraction. So as shown here, that our model outperforms all these classifiers, and this verifies the stability and the performance of this model. To conclude, in this work, we have used supervised and unsupervised learning for network traffic classification. Then, to improve the performance of the feature extracted through our model and to avoid overfitting, we have injected the dropout and the noise encode hyperparameter. And as future work, we plan to use a much larger amount of available data to verify its impact on the classification performance. Thank you for your attention.
Right. Thank you all for this interesting talk. Questions. We have time for a couple of questions. While others is preparing, I'll start asking a question here. Is there a specific reason that you use the autoencoder in your classification problem? Is it because it's only using unsupervised learning, or is there any other narrow models you can utilize here in classification, in your classification problem?
I can't hear you.
Okay. My question. Let me repeat the question. So my question is there any reason that you use the autoencoder as your classification model? Can you hear me?
Same problem, I can't hear.
Can you read the session Q&A? I can type my question there.
Can you write
Can you read the Q&A question?
No, I can't hear.
You still can't hear me? Can you hear me?
Yes.
Okay. My question is there any reason for using the autoencoder as the classification model?
Yes, we have used autoencoder to use the unlabeled data, and as you know that the unlabeled data can provide informative characteristics. So based on the literature review, we find that the researcher used just the labeled data. So we have tried to combine the labeled and unlabeled data. So that's why we have used the staked sparse autoencoder to extract the relevant feature, and then to classify with labeled data.
Is there any other classifiers or classification models that could be used here? Have you compared with any other classification models that use also unlabeled data?
No, but in the future we plan to use autoencoder or other version of autoencoder, not just staked sparse autoencoder. So now we have compared with the reference classifier, random forest, SVM, and decision tree. Also, we compared with the staked sparse autoencoder without the dropout and the noise hyperparameter. But as future work, we plan to use other model to verify the performance of this model. And to improve also we can improve the performance of this model to use the other large amount of available data and see the impact of the number of the amount of available data.
All right, thank you. Any further questions from the audience? Okay, have one more question, if time permit. I see in your experiments, your data consists of about 70% labeled and 30% unlabeled, right? Have you tried to test or evaluate the sensitivity of your classifiers if you change the percentage of labeled versus unlabeled?
No,
Like what if you have more unlabeled data, like more percentage, like 50% unlabeled? How your system will perform here?
so really, I indicate this in the future work, in the conclusions that I will vary the number of the amount of available data to verify its impact on the classification. But in this version, no, I didn't do this.
Okay, I see. Thank you.
Thank you.
Right. I think we reached to the end of the first technical